Ceres, the Solar System's Hidden World Part 1, Discovery and Naming. In the early 1800s, a mystery lurked in the skies between Mars and Jupiter. Astronomers suspected a hidden world in that gap hinted at by an old rule called the Titius-Bode Law. A group nicknamed the Celestial Police began a systematic search for this missing planet. On January 1801 at the Palermo Observatory in Sicily, Italian priest astronomer Giuseppe Piazzi recorded a faint point of light that stood out among the stars. Piazzi watched this tiny speck night after night. It moved steadily in a circular path. At first, he thought it might be a comet because it had a slight fuzz and no fixed place like a star. But as January turned to February, he realized this object was something new, a little world orbiting the Sun. By late January, he understood he had discovered an entirely new kind of object in the solar system. Excitement followed quickly. Piazzi decided to name his discovery after Ceres, the Roman goddess of agriculture, whose temple was in Sicily. He added Ferdinandia to honor his king, but that part of the name was later dropped. Other astronomers had briefly called it Hera or Juno, but in the end the name Ceres stuck. Newspapers and astronomers announced the discovery as a new planet, and people were thrilled. Just weeks later, after only a few months of observation, Ceres slipped into the sun's glare and seemed lost. Astronomers worried they would never find it again. Enter Carl Friedrich Gauss, a brilliant young mathematician. Using Piazzi's data, Gauss invented a new method to predict Ceres' orbit. On December 3, 1801, Gauss's calculation paid off. Ceres was found exactly where his math said it would be. Ceres was indeed orbiting the Sun in a regular path and was not an ordinary comet. Soon, more objects were found in the same region of space. Astronomer William Herschel suggested calling these tiny worlds asteroids, meaning star-like bodies. Ceres was catalogued as the first asteroid officially named 1 Ceres. Yet it was far larger and rounder than the others, about 940 kilometers across, so massive that it held a nearly spherical shape. The discovery of Ceres revealed the existence of the asteroid belt and opened a new chapter in solar system exploration. Its story was just beginning, from its icy interior to the bright salt deposits on its surface. Ceres' surface gravity is very weak, only about 0.27 meters per second squared. That is roughly 1/38 of Earth's gravity. In practical terms, if you could stand on Ceres, you would weigh only a few percent of your Earth weight. For example, a 100-kilogram person would feel like they weigh just 2.7 kilograms on Ceres. This low gravity means that anything on Ceres' surface rocks dust. Even a person could easily be thrown off into space with a strong jump or blow. The escape velocity from Ceres is also small, about 0.51 kilometers per second, so spacecraft don't need much thrust to leave its gravity. Rotation-wise, Ceres spins relatively quickly. It completes one full turn one day in just about 9 hours. This fast rotation is actually one of the shortest days of any body in the solar system. Because of this short day, the Sun moves quickly across the sky on Ceres, less than half as long from sunrise to sunrise as on Earth. The spin axis of Ceres is tilted only about 4 degrees from perpendicular to its orbit. This tiny tilt means Ceres has almost no seasons, unlike Earth or Mars' sunlight doesn't move much north or south on Ceres over its year. Every day and night on Ceres feels pretty much the same, just shorter, no matter where you are on the surface. Because Ceres has no moons, there are no tidal forces from satellites to slow or lock its rotation. Its spin remains consistent, and the combination of rapid rotation and low gravity gives Ceres a slight bulge at the equator. Observations by the Dawn spacecraft and ground telescopes confirm Ceres is nearly round, bulging only a bit around the middle due to rotation. In summary, Ceres travels a lonely path around the Sun, about 2.8 AU out on average, taking 4.6 years per orbit. It is about 940 kilometers across, with a mass of approximately 9.4 times 10 to the 20th power kilograms. Its gravity is gentle, approximately 0.27 meters per second squared, and it spins on its axis every about 9 hours. Together, these numbers give us a picture of Ceres as a world much smaller and weaker than a planet, yet still the heavyweight champion of the asteroid belt. Beneath the surface of Ceres, imagine peeling back the crust of a strange new world. Ceres, That lonely dwarf planet circling between Mars and Jupiter may look like a lifeless rock from afar, but beneath its dusty exterior lies an astonishing secret. Scientists now believe Ceres is not a simple stone but a layered world of rock and ice. At its core, a dense heart of rock is thought to sit under a thick shell of water ice, all capped by a rocky, salty crust. Let's journey down through Ceres' hidden layers to see what lies inside and how we know. The innermost region of Ceres is thought to be a rocky core. Picture the heaviest ingredients in a batter sinking to the bottom of a mixing bowl. That's what happened here. When Ceres formed, heat from radioactive elements likely melted some of its ice. Denser silicate minerals rock sank toward the center, forming a compact core hundreds of miles across. This is no metal core like Earth's. Ceres never got hot enough to melt iron, but a solid mash of carbon-rich, rocky material. Encasing this core is a vast mantle of ice and water. In fact, models suggest Ceres might be roughly half ice by volume, though ice is lighter, so it's about a quarter of its mass. Imagine an ocean frozen solid beneath the surface, hundreds of millions of cubic kilometers of water locked up as ice and salty slush. To put that in perspective, that could be more fresh water than all of Earth's lakes and rivers combined. Covering all this is the outer crust, a thin, dusty skin of rock and clay, dark from carbon-rich minerals. In places it's streaked with bright salt deposits, evidence that liquid water once seeped up through cracks and evaporated, leaving minerals behind. How do we know Ceres is layered like this? The clues came from its density, its shape, and subtle shifts in spacecraft orbits. Ceres' average density is only about 2.16 grams per cubic centimeter, much lower than most rocky worlds. That tells us Ceres must contain lots of something lighter than rock, namely water ice. From that simple number, scientists infer roughly 25% of Ceres' mass is water. But they needed more evidence to map the layers. Enter NASA's Dawn spacecraft. As Dawn orbited Ceres, its trajectory was gently tugged by the dwarf planet's gravity. By tracking tiny variations in Dawn's speed and orbit, scientists weighed Ceres in detail. The gravity data showed that Ceres is in hydrostatic equilibrium, essentially. It's rounded just the way a fluid body would be. That means its interior is soft enough to flow slightly under its own weight. If Ceres were a rigid rock, mountains and basins would distort its shape much more. Instead, the dwarf planet is almost perfectly spherical, only a little bulged at the equator by its 9-hour spin. This spherical shape is a hallmark of a differentiated body, one that once had enough internal heat to rearrange its insides. In other words, Dawn's measurements confirm Ceres has distinct layers. One of the most telling signs comes from how Ceres' topography floats on its interior. For example, the huge mountain Ahuna Mons, a towering icy peak, is surprisingly stable for its height. On a solid rock world, such a mountain would collapse under its own weight. But on Ceres, it's as if Ahuna Mons is sitting on a soft cushion of ice. More generally, Dawn found that high elevation regions seem to displace mass below them, much like the way a heavy ship sinks into water. In geologic terms, this is isostasy. The crust and mountains adjust so that thick or heavy areas float higher. This can only happen if the layer beneath the mantle is weak enough to flow. On Earth this happens too, but on Ceres it's more dramatic because the ice rock mantle is much softer. These gravity and shape clues tell the tale. Heavy rock has partially sunk inward, light ice has risen, and the boundaries between layers are blurred. Unlike Earth's sharp core mantle crust divisions, Ceres layers are more like a gradient. We also learn from Ceres' thermal history. Early in its life, heat from radioactive isotopes like aluminum-26 likely warmed Ceres' interior. Water ice began to melt and mingle with rock, and kind of global muddy ocean formed beneath the cold crust. This ocean eventually froze as Ceres cooled, solidifying the icy mantle, but it never got hot enough to create a volcanic silicate magma-driven world. Instead, Ceres remained a partly frozen world where water and rock interacted quietly. The chemistry on the surface backs this up. Dawn spotted clay minerals and salts that only form in the presence of water. These minerals suggest that, billions of years ago, liquid water circulated through Ceres rock. Even today, heat from deeper inside plus the presence of salts that lower freezing points might keep pockets of briny water or mush alive under the ice. In fact, a recent study proposes that a subsurface reservoir of brine could still lurk beneath Ceres, slowly leaking tiny amounts of water vapor into space and occasionally erupting as minor cryovolcanic activity. If true, Ceres is essentially a frozen world with a lingering secret ocean. All these pieces fit a remarkable picture. Ceres is a water-rich, layered dwarf planet. Its very low density and spherical shape are the first clues, pointing to a massive ice component. The gravity data from Dawn then confirmed that this ice isn't evenly mixed but layered, with heavy materials toward the center. The bumps and depressions on the surface respond as if they sit atop a squishy interior. Thermal models of Ceres' birth show it was warm enough to partially differentiate, but not hot enough to boil away all its water or form an iron core. The result is a gentle onion of rock and ice, still evolving over time. In storytelling terms, Ceres' interior is an epic finale. Unlike dead, dry asteroids, Ceres likely had an ancient ocean and could still harbor hidden brine. Scientists now think its core is a rocky hatchery surrounded by an ocean of ice, a far cry from what we imagined before Dawn's visit. This knowledge has transformed Ceres from a simple asteroid into a world more akin to a miniature, frigid ocean planet. Beneath that plain grey surface, Ceres holds a trove of ice and a history of heat and water. In the quiet aftermath of its tumultuous youth, Ceres' layered interior stands as a testament to its complex history. It reminds us that even small worlds can be full of surprising secrets, and that sometimes the most extraordinary stories are hiding right beneath our feet. The surface of Ceres, colors, craters, and clues. From a distance, Ceres looks like a plain grey pebble in the asteroid belt. But up close, its surface is surprisingly varied. Overall, it appears dull and dusty, a muddy grey-beige sphere, like weathered concrete. Color maps reveal subtle tones. Some areas are slightly reddish or brownish, hinting at clay and carbon-rich rock, while others appear bluish where fresher material or ice lurk. In true color images, Ceres comes out as a pale yellow-brown world. In other words, imagine an old rocky desert, mostly grey and brown, but with occasional streaks and patches of different hues. One striking contrast on this monochrome canvas is the brilliant white spots, like someone splattered salt or chalk on the surface. These bright spots stand out sharply against the dull background, hinting that something unusual is happening beneath. Impact craters and basins. Ceres' surface is pockmarked with craters of all sizes, from tiny pits to vast basins. Some craters have steep, sharp rims, others are more worn and shallow. The variety tells us its crust contains a lot of ice which flows and relaxes over time. Among the most prominent craters and basins are Acacia crater sheer 90 kilometers across. This is the home of Ceres' famous bright spots. About 4 kilometers deep, Acacia's floor holds dazzling salt deposits and even appears to emit a faint haze of vapor, as if it briefly breathes water into space. Hawlani crater, 70 kilometers. A relatively small, young crater with very bright walls and floor. Its fresh appearance with crisp edges and landslide gullies makes it highly reflective and unusually cold. Urvra crater, lose 160 kilometers, one of Ceres' giants. It's deep around 6 kilometers and boasts a high central peak, a jagged mountain rising roughly 3 kilometers from the floor. It's a dramatic feature carved into the southern terrain. Dantu and Ezinutu, 120 kilometers each, two deep basins in the south, each about 5 kilometers deep. They expose rugged walls and show many layers of ice-rich crust. Kirwan and Yallow Day 200 plus km, the largest impact basins on Ceres, more than twice the size of Dantu. Surprisingly, they are shallower and smoother than smaller craters. This suggests their floors have relaxed. The icy crust flowed to partially fill them over geological time. Each crater tells a story. For example, the huge Kirwan impact long ago might even have sent shockwaves through Ceres, affecting features on the opposite side. The mix of sharp and softened rims, deep and shallow basins, reveals an icy world that holds clues to its inner layers. The bright salt patches. Perhaps the most startling discovery on Ceres came from the bright spots seen in Acacia and elsewhere. In normal light, they look like patches of pure snow or salt. Dawn spacecraft observations explained the mystery. These spots are salt deposits, not ice. In fact, they are mainly sodium carbonate, a kind of salt that forms when briny water evaporates. In a crater's center lie two big salt lakes, Cerealia Facula in the middle and Venalia Faculae, a smaller cluster to the east. Dawn's team found these salt flats must have come from briny water rising up from deep underground. The idea is that Ceres once had, and may still have, a hidden reservoir of salty water below its crust. When this brine seeped through cracks to the surface and then vaporized, it left behind a bright crust of salt. Today the effects are still visible. A crater's floor still glows whitely under sunlight, and tiny wisps of water vapor have even been detected above it. In other words, a crater occasionally vents a fleeting plume into space, as if the dwarf planet were quietly outgazing. Besides a crater, small craters like Haulani and Oxo also have minor bright patches or icy material, showing that salt and ice exposure is scattered around. All these shining spots are like neon signs announcing that Ceres' interior once let liquid water reach the surface. They hint that something dynamic happened, and perhaps still happens under the surface, something more than just frozen rock. Icy landslides and flows. Dawn's cameras also captured landslides and flow features on Ceres that look eerily familiar. On steep crater walls and slopes, there are streaky trails of displaced debris. Some of these are so smooth and rounded that they resemble rock glaciers or icy avalanches on Earth. Scientists categorize them roughly into types. Rock glacier flows. These are broad, tongue-shaped landslides with a bulging two at the bottom, often seen in higher latitudes. They look like glacial ice mixed with rock, creeping slowly downhill. Avalanche slides, narrow, elongated streaks of material that have slid down steep slopes. They resemble classic landslides or avalanches, but on icy ground. Fluidized ejecta flows. Around some fresh craters you can spot smoother, splash-like lobes of debris. These appear as if the impact melted a bit of ice into mud that flowed out and settled in lobes around the crater. These icy slides tell us that Ceres' crust is not hard and inert. The presence of thick lobat debris flows implies there is a significant amount of ice in the ground, making it weak and flowable. In short, Ceres can have glaciers or mud like ice landslides, even though it's much smaller and colder than Earth. The surface is dynamic enough that gravity-driven flows can reshape it. Hidden ice and water vapor. Another clue to Ceres' hidden water comes from its polar craters. Near the poles, some crater floors lie in permanent shadow and act as cold traps. Dawn observed that these shadowed pockets contain bright patches of nearly pure ice. Because Ceres is small and its tilt changes, sunlight sometimes peeks in, so exposed ice would normally evaporate in a few years. Studies indicate that the ice in these craters must be extremely young, likely only a few thousand years old at most. That implies the ice is being refreshed. New water ice is exposed or deposited regularly. How? Possibly new impacts or collapses churn up fresh icy material that then refreezes in the shade. We also know Ceres occasionally releases water vapor. Telescopes and Dawn data have detected tiny outbursts of water gas from its surface, probably around a crater or other active areas. Although the atmosphere is just a whisper, it's real. This means that deep Ceres must still harbor liquid or slushy water that can evaporate into space. In summary, Ceres has ice hidden just below its dusty surface, and events like impacts or internal activity can uncover it and even send a brief mist of vapor upward. The polar ice patches and vapor plumes are like a fresh snowfall on a warmer moon, proof that water is still on the move. Uhuna Mons, the lone cryovolcano, towering above the cratered plains of Ceres, is Uhuna Mons, a solitary mountain unlike any other on this world. It rises about 4 kilometers, 2.5 miles high with smooth, sloping sides. At its summit and down its flanks are streaks of bright white salt, the same kind as in a crater. Remarkably, Uhuna Mons has almost no impact craters of its own, which tells us it formed fairly recently in geological terms. All these facts point to a surprising conclusion. Uhuna Mons is an ice volcano, or cryovolcano, not an ordinary rocky peak. Researchers believe it was built by an eruption of icy mud from deep inside Ceres. Imagine a volcano on Earth spewing slushy mud laced with salt instead of molten lava. That's essentially what happened on Ceres. Key features of Ahuna Mons. Height: it's about 4 kilometers tall, making it the tallest mountain on Ceres. Shape: a smooth dome-like peak, standing alone amid the flatter terrain. Bright streaks: long lines of salt run down its sides, evidence of erupted briny material. Youth: virtually crater-free, so it must be relatively young, only a few 100 million years old at most. Origin: formed by cryovolcanism, an eruption of icy, salty lava from the interior. Some scientists even suggest that shockwaves from the huge Kerwan impact on the opposite side of Ceres helped trigger its rise. Ahuna Mons is like Ceres' secret volcano, except it is made of ice and salts, not rock. Its existence is one of the clearest signs that Ceres' interior was active. Not only did liquids move underground, but they actually erupted and built a mountain. Clues to an active interior: all these surface wonders, the bright salt flats, the flow like landslides, the patchy ice and plumes, and the lone ice volcano, weave together a simple message. Ceres still holds something of a living interior. Here's what the clues tell us. Salt deposits. The gleaming salting craters shows that liquid brine once seeped up from deep below. You don't get salt flats without water. Cryovolcano Ahuna Mons. A mountain built by icy magma means there must be heat and liquid under the crust driving eruptions. Icy flows. Landslides that behave like glaciers or slush indicate the crust is rich in ice and can move. Young ice and vapor. Newly exposed ice and occasional water vapor suggest water is still cycling to the surface even today. Taken together, these features imply that Ceres isn't just a cold, dead rock. It likely has, or had until recently, a warmish interior layer where salty water or slushy ice can slowly circulate. Radioactive decay and leftover heat from its formation could be enough to keep pockets of the dwarf planet thawed or soft. In effect, Ceres behaves in some ways like a small ocean world, only with water trapped under ice. In the end, Ceres' landscape reads like a mystery novel. Every crater, streak, and hill offers a clue. The drab grey surface belies a surprisingly complex world. From afar it looked like a simple asteroid. Up close it reveals hidden water, glaciers, and volcanoes of ice. These signs of past and perhaps ongoing activity make Ceres one of the most intriguing bodies in our solar system, a dwarf planet with a quietly active heart. Water, salts, organics, and the possibility of life on Ceres. When NASA's Dawn spacecraft first approached Ceres, no one expected this dim, grey dwarf planet to become one of the most intriguing candidates in the search for habitability. But once we started peeling back the layers of data, a remarkable picture emerged. Ceres is a world shaped by water, rich in salts, and even organic molecules, the very building blocks of life. Let's explore what that means, and why tiny Ceres has become such a big topic in astrobiology. A world rich in water. Ceres contains a surprising amount of water, far more than most asteroids and even more than some moons. It stores water in 3 main forms. 1. Frozen ice beneath the surface. Almost everywhere Dawn looked, it found signs of buried ice just a few meters to a few kilometers below the crust. The crust itself is a mixture of rock, salts, and ice, something like a frozen, salty clay. Some craters near the poles contain permanent shadows where the sun never shines. In these dark pockets, patches of almost pure ice survive for thousands of years. This ice is so bright and fresh looking that scientists believe it must be constantly replenished, suggesting that Ceres is still active beneath the surface. 2. Hidden underground brines. Even more exciting is the evidence for briny liquid water deep underground. Salt water doesn't freeze as easily as pure water, and the salts on Ceres, like sodium carbonate, are extremely good at staying liquid even at very low temperatures. That means that pockets of Ceres' interior could still be warm enough for slushy, salty liquids to exist today. The bright spots in Ocata crater are a direct clue. Those salts didn't form billions of years ago. They are young on geological timescales, possibly only a few million years old. Something in Ceres' interior pushed brine up toward the surface and left those glowing white deposits behind. 3. Water vapor escaping into space. Occasional detections of faint water vapor near Ceres suggest that brines may still seep upward and evaporate into space, a gentle whisper-like hint that the dwarf planet may not be completely frozen inside. A landscape painted with salts. The salt deposits on Ceres are among the brightest features in the entire asteroid belt. These salts are primarily sodium carbonate and ammonium-based salts, minerals that form when salty water evaporates. Why is this so important? Because these minerals require liquid water to exist at all. Their presence on the surface means Ceres once had sustained liquid environments. Underground reservoirs likely interacted with rock. Water was chemically active, not just frozen and inert. In other words, Ceres had the ingredients for complex chemistry. These salts are also similar to those found around Earth's hydrothermal systems, environments known for supporting microbial life. The discovery of organic molecules. One of the most surprising findings came from a region near Ernetek crater, where Dawn detected organic molecules spread across several square kilometers. These organics include complex carbon-based compounds similar to those found in primitive meteorites. Why does this matter? Because organics are the foundation of biology. While the discovery does not prove life, it shows that Ceres naturally produces or preserves the same kinds of molecules that helped seed early Earth. Even more interesting, the organics on Ceres appear to be native, not delivered by a meteorite. That means they likely formed through internal processes, perhaps in warm, water-rich environments beneath the surface. Could Ceres support life? Let's be clear, no one is saying Ceres has life. But the question of habitability, whether a world could support life, is where Ceres becomes incredibly exciting. For life as we know it, you need 3 things. 1. Liquid water. Ceres has it at least in briny pockets. The evidence for ancient and possibly current brines puts Ceres in the same category as Europa or Enceladus, though on a smaller scale. 2. Essential chemistry. Ceres has it. Salts, clays, organics, everything needed for chemical reactions that could support life is present. 3. Energy. Ceres likely had it. Radioactive elements in the core and the decay of heat would have powered warm environments for millions of years. Large impacts may also create temporary warm niches, and cryovolcanism suggests internal movement and heat are still present. In short, Ceres ticks every major box scientists use when evaluating whether a world might once have been habitable. While Earth-like life on the surface is impossible today, too cold, and too exposed to radiation, tiny microbial life in subsurface brine pockets is not out of the question. If Ceres ever had warm, salty reservoirs long enough, it could have hosted simple chemistry or even primitive organisms. We do not know yet, but the possibility is worth exploring. Why this matters? Ceres shows us that life might not require a large, warm Earth-like planet. Sometimes, small worlds, cold on the outside but warm and wet inside, may have all the right ingredients. If Ceres had long-lasting briny oceans or chemical-rich pockets underground, it may have been one of the many small laboratories where nature experimented with the early steps toward life. And who knows? Perhaps traces of those ancient environments still remain, locked in salt crystals or frozen in the layers below. The Dawn mission, unlocking the secrets of Ceres. For most of human history, Ceres was nothing more than a faint point of light in the night sky, a small, mysterious speck hidden between Mars and Jupiter. Then, in 2015, everything changed. NASA's Dawn spacecraft arrived, becoming the first mission ever to orbit a dwarf planet and the first to explore 2 worlds in one journey. Its arrival at Ceres transformed this once unknown object into one of the most fascinating bodies in our solar system. Let's step into Dawn's story, the mission that rewrote the textbooks on planetary science. A journey powered by ion engines. Dawn was unlike any spacecraft before it. Instead of using powerful chemical rockets, it used ion propulsion, a gentle blue glow of electrically charged xenon ions that provided a continual, efficient push. This futuristic engine allowed Dawn to do something never achieved before: visit Vesta, leave its orbit, then travel on to Ceres. This made the mission a true trailblazer. After studying Vesta, Dawn fired its ion engines and began a 2.5-year cruise towards Ceres. Slowly, gracefully, it spiraled into orbit around the dwarf planet in March 2015. At first, Ceres looked like a blurry sphere, but as Dawn descended into lower orbits, details sharpened, and then came the surprises. The first surprises: bright spots and unexpected activity. Even before Dawn arrived, telescopes had noticed something odd on Ceres, glaring bright spots reflecting sunlight as if mirrors were embedded in the crater floors. But no one knew what they were. When Dawn finally got close enough to see them clearly, the world was stunned. The bright spots inside a crater looked almost artificial, glowing, crisp, and astonishingly white. Some scientists compared them to headlights shining across a grey desert. These turned out to be salt deposits, left behind by briny water that seeped up from deep underground and evaporated. The more Dawn studied them, the stranger Ceres became, mapping a frozen, complex surface. As Dawn orbited Ceres at various altitudes, it built a complete 3D map of the dwarf planet. It revealed a crust rich in clay minerals, large amounts of buried ice, evidence of ancient water flows, surface features hinting at internal heat. The minerals Dawn detected, including sodium carbonates and ammonium salts, are not common on dry, dead asteroids. They form in environments where water interacts with rock. This discovery alone changed everything, suggesting Ceres had once been warm enough to sustain liquid water for a long time. The mystery of Ahuna Mons. One of Dawn's most dramatic findings was Ahuna Mons, a smooth, icy mountain towering 4 kilometers above the surrounding plains. It had virtually no impact craters, bright streaks of salt running down its slopes, a dome-like shape consistent with cryovolcanic activity. In plain terms, Ahuna Mons is an ice volcano, evidence that Ceres didn't freeze solid billions of years ago. Instead, its interior remained warm enough for briny material to push upward and erupt at the surface. Nothing like Ahuna Mons had ever been seen in the asteroid belt. Evidence of a hidden brine reservoir. Over time, Dawn lowered itself into its tightest orbit, just 35 kilometers above the surface. At this altitude, it collected incredibly detailed gravity and mineral data. These measurements revealed something extraordinary. Beneath a crater, deep underground, there appears to be a massive reservoir of salty water. Not a global ocean like Europa's, but a regional pocket of brine that might still have been liquid in the geologically recent past. Some studies even suggest that thin layers of brine could still exist today under certain conditions. If true, Ceres may be one of the closest bodies to Earth with active underground liquids. Dawn's final moments. After months of close observation, Dawn's hydrazine fuel, used for pointing the spacecraft, finally ran out. When that happened, Dawn could no longer control its orientation or communicate with Earth. NASA made a deliberate choice: leave Dawn in orbit around Ceres forever to avoid contaminating the dwarf planet with Earth microbes. If life could ever exist on Ceres, even in microscopic form, it must be protected. And so, Dawn now silently circles the dwarf planet, its mission complete, but its legacy alive. A mission that changed our understanding. Before Dawn, Ceres was little more than a footnote in astronomy textbooks. After Dawn, it became a world of vast ice reserves, strange salty plains, cryovolcanoes, complex chemistry, possible underground brine pockets, and potential for habitability. It forced scientists to rethink what small worlds can be, not just leftovers from planet formation, but active, evolving bodies with internal heat, water, and fascinating geology. Dawn didn't just explore Ceres. It revealed Ceres and showed us that even the smallest worlds can hold the biggest surprises. Ceres and the story of the early solar system. Ceres may be small, but it tells a story far larger than itself. A story about the earliest days of the solar system, when planets were still forming, colliding and evolving. In many ways, Ceres is a time capsule, a preserved remnant from a period long before Earth had oceans or a stable crust. Understanding Ceres helps us understand how planets are born, how water spreads across space, and why worlds evolve so differently. This dwarf planet is not just an isolated curiosity, It's a missing chapter in the solar system's history. A survivor from the planet-building era. To see Ceres properly, imagine the solar system 4.5 billion years ago. Dust, ice, and rock were swirling in a vast disk around the young sun. Through countless collisions, small pieces stuck together, forming larger and larger bodies, the planetary building blocks, known as planetesimals. Most of these early objects merged to form the planets we know today. But Ceres never joined that violent race. It grew large enough to become spherical and internally layered, but not large enough to become a full planet. It is, essentially, a frozen embryo of a planet, a world that began the journey toward planethood but never finished. And because it avoided catastrophic collisions that reshaped many other objects, Ceres preserved ancient materials and structures that would have otherwise been destroyed. This makes Ceres one of the most scientifically valuable relics in the solar system. Why Ceres is unlike anything else in the asteroid belt. Most asteroids are small, dry, and solid rock, leftovers shattered by billions of impacts. Ceres is different. It's massive, making up nearly 1/3 of the entire asteroid belt's mass. It's spherical, meaning gravity shaped it like a planet. It has water, ice, and salts, materials rare among typical asteroids. It has internal layering, like a miniature world. It has organic molecules, unlike most rocky asteroids. This tells scientists something crucial. Ceres formed in a region of the solar system where water-rich material was abundant. Either it formed farther from the Sun and migrated inward, or icy material drifted into the asteroid belt from beyond Jupiter. Whichever scenario is true, Ceres is a window into how water traveled across the inner solar system, possibly even delivering water to Earth. A key to understanding water in the inner solar system. One of the great mysteries of planetary science is how Earth became a water-rich world. Early Earth was too hot for water to condense, so scientists believe icy bodies from farther out brought water inward. Ceres supports this idea beautifully. Its mixture of water ice, clays, salts, carbon-rich minerals matches the chemistry found in meteorites that have struck Earth. These meteorites, called carbonaceous chondrites, are thought to be ancient fragments from bodies similar to Ceres. This means Ceres may be one of the prototypes of the objects that watered the early Earth, helping to create oceans, rivers, and perhaps even the conditions for life. In this way, Ceres may have played a quiet but profound role in Earth's history, a small world with planet-like processes. Ceres also challenges our idea of what a small world can be. We usually imagine big planets as dynamic and small objects as frozen and dead, but Ceres breaks that rule. Despite its size, Ceres shows signs of internal heating, chemical alteration by water, cryovolcanic activity, volatile movement under the crust, a long-lived subsurface reservoir of brine. These are planetary processes, not asteroid processes. Ceres demonstrates that even objects as small as 1,000 kilometers wide can differentiate, evolve, and remain active for billions of years if they contain enough water and heat. This expands our understanding of what worlds might be habitable. It tells us that life might not require large Earth-like planets. Small, icy bodies could have supported warm, chemical-rich environments in the past. What Ceres tells us about planetary diversity? When comparing Ceres to other worlds, it occupies a unique place. It's not like dry, rocky Vesta. It's not like icy moons with global oceans. It's not like comets filled with volatile ices. And it's not like terrestrial planets with molten cores. Ceres is something in between, a hybrid object, a rocky icy dwarf planet with elements of asteroids, moons, and planets all combined. This middle ground makes Ceres scientifically precious. It reveals the continuum of bodies that formed in our solar system, showing that planets didn't appear fully formed but evolved through a spectrum of intermediate stages. A lens into the solar system's earliest chemistry. Before planets existed, the solar system was dominated by small, watery, organic-rich worlds. Ceres may be the best preserved example of that environment. Its minerals tell us what the solar system was made of when everything was still forming. By studying Ceres's chemistry, scientists gain clues about early water-rock reactions, The distribution of organic molecules, the temperatures in the solar nebula, how heat shapes small bodies, how primitive oceans formed and froze. Ceres, in essence, is a laboratory frozen in time, a story still being written. Perhaps the most fascinating part is this: Ceres is still evolving. Its surface changes slowly. Salt deposits appear younger than the surrounding terrain. Brines may still exist underground, and the dwarf planet may occasionally release water vapor into space. What we see today is not just a fossil, it's a world that continues to shape itself over time. Ceres tells the story of how worlds form, how they change, and how water and chemistry spread across space. It bridges the gap between asteroids and planets, between frozen ice and warm brine, between ancient history and ongoing activity. It's a reminder that even the smallest worlds can hold the biggest secrets, and that the history of the solar system is written not only in planets, but in the quiet, overlooked worlds that orbit between them. The future of Ceres, missions, exploration, and the promise of a new frontier. As Dawn completed its historic mission, it left us not with answers, but with bigger, bolder questions. Ceres is no longer just a forgotten dwarf planet in the asteroid belt. It has become a destination, a future outpost, and a key piece in humanity's plans to explore deeper into the solar system. What comes next could reshape not only science, but the future of space exploration itself. Ceres as the gateway to the outer solar system. Imagine the solar system as a vast ocean. If Mars is the first island, then Ceres may be the gateway, a natural refueling point for journeys farther out. Why? Because Ceres has what spacecraft and future explorers desperately need: water. And in space, water is everything. Water ice can be converted into liquid water for drinking and agriculture, oxygen for breathable air, hydrogen for rocket fuel. This turns Ceres into a potential interplanetary gas station. A base on Ceres could mine ice, break it apart using solar-powered electrolysis, and launch missions deeper toward Jupiter, Saturn, and beyond, at a fraction of the cost of launching from Earth. Its low gravity makes takeoff incredibly cheap. Its ice makes refueling sustainable. Ceres could someday become a hub for exploring the outer solar system. Future missions, what we want to know next. Although Dawn revealed a world rich with mysteries, it was only the beginning. Several mission concepts are already being discussed. 1. A Ceres sample return mission, the holy grail of planetary science. Imagine bringing salty deposits or organic-rich material from a new tech crater back to Earth. With modern laboratories, scientists could test whether subsurface brines still exist, how organics formed, whether amino acids or prebiotic molecules are present, whether the salts contain trapped gases or biomarkers. A single return sample could revolutionize astrobiology. 2. A cryobot or ice drilling lander. What lies beneath the crust? We know Ceres has subsurface ice, but is there liquid brine today? A lander equipped with a heated drill or a melting cryobot could reach several meters below the surface to detect liquid pockets, chemical gradients, heat sources, possible microbial-friendly environments. Ceres is easier to land on than Europa or Enceladus, making it a perfect testbed for deep ice exploration. 3. An orbiter with modern instruments. A next-generation orbiter could map Ceres with far higher resolution. Key questions remain. How long ago was Ahuna Mons active? Are small cryovolcanoes still erupting brine today? Does Ceres have a weak, temporary atmosphere? Where exactly is the underground brine reservoir? New instruments could also detect seismic activity, tiny moonquakes that reveal movement beneath the surface. Could humans one day live on Ceres? It may sound like science fiction, but Ceres is considered one of the best potential sites for human settlement beyond Mars. Here's why. 1. Gravity that is gentle but useful. Ceres' gravity is about 3% of Earth's. This is low enough for easy construction and transport, but high enough that long-term human health might be more manageable than on microgravity spacecraft. 2. An abundance of ice. Water is the most important resource for habitation. With enough ice to sustain generations, Ceres could support closed-loop life support systems, greenhouses, and manufacturing. 3. Protection below the surface. Radiation is one of the biggest dangers for deep space habitation. Ceres' crust is thick enough that underground habitats, built inside lava tubes or excavated chambers, could protect settlers from cosmic rays. 4. Industrial potential. Ceres is rich in carbon, nitrogen, ammonia, water, salts, clays. These ingredients are perfect for producing plastics, fertilizers, fuels, ceramics, and other essential materials. Ceres could host self-sustaining colonies that operate independently of Earth, a strategic outpost in space. As humanity pushes outward, logistics become everything. The asteroid belt contains unimaginable resources, metals, minerals, water, and Ceres sits at the center of it all. A future Ceres outpost could serve as a mining hub, a research station, a refueling depot, a manufacturing center, a launch platform for missions to the outer planets. Its low gravity and abundant water make it far more practical than the Moon or Mars for deep space logistics. Some long-term visions even propose space elevators on Ceres, something impossible on Earth but achievable on such a low-gravity world. With such infrastructure, transporting materials to orbit would be incredibly cheap. The big question? Life. But beyond resources and engineering dreams lies the deepest question of all. Could Ceres harbor life, or the remnants of it, if future missions find preserved microbes, organic molecules in specific patterns, fossil-like textures within salt deposits, or chemical signatures of biological activity? Then Ceres could become one of the most important scientific sites in human history. Even if life never existed there, understanding why it didn't despite the presence of water, heat, chemistry, and organics would reshape our theories of how life begins. Ceres challenges the boundaries between dead asteroid and living planet, and that makes it essential. A new frontier awaits. Ceres began as a blurry point of light in 1801. 2 centuries later, it stands as a world full of promise, the key to understanding how planets form, how water travels through space, and where life might emerge beyond Earth. The future of Ceres is not written yet, but one thing is certain: it will play a role in humanity's journey across the solar system as a laboratory, a resource haven, a stepping stone, and perhaps one day a home. Ceres is no longer just a destination. It is a frontier waiting for the next chapter to begin.